Starting today, let's talk a bit about the current state of physics. If you want to know what the world is really made of, only physics can give you the ultimate answer. Physics is the most revolutionary of sciences. It has overturned our understanding of the world time and time again, producing theories that boggle the mind and attracting countless brilliant minds to devote their lives to it. Modern science fiction is not only directly inspired by physics but, in fact, has never been as wild as the imaginations of physicists themselves. But if you once dreamed of becoming a physicist to explore the ultimate secrets of the universe, yet didn't manage to do so for various reasons, you may not need to feel too much regret. Because in the past few decades, physics has made no major breakthroughs. Our worldview hasn't been updated for a long time. To put it bluntly, physics has hit a wall. We'll first review the major revolutions in physics, then look at its current state, and finally speculate about its future, focusing on how physics has changed humanity's worldview. Unfortunately, we were not born in an era when physics was making rapid leaps forward, and it might never advance like that again. In 1609 CE, Wanli 37 of the Ming dynasty, Italian mathematician and astronomer, Galileo received a new instrument from the Netherlands, the telescope. The Dutch originally used it for navigation or, occasionally, spying on the neighbors. Galileo, being skilled with his hands, quickly improved it to achieve 20 times magnification. This allowed him to use the telescope to observe celestial bodies. Galileo immediately saw things that were utterly shocking. In March 1610, he hurriedly published a slim 60-page book, Sidereus Nuncius, the Starry Messenger. This book completely overturned humanity's understanding of the world. At the time, the mainstream cosmology held that all heavenly bodies revolved around the earth in perfect circles, and that these bodies were smooth, glowing spheres. The Catholic Church taught that only earth was imperfect, full of pits and flaws, while the heavens were sacred and flawless. However, in the Starry Messenger, Galileo announced 4 revolutionary discoveries. 1. The moon's surface is not perfect. Galileo accurately sketched what he saw through the telescope: mountains and craters and uneven terrain. The heavenly bodies were not smooth and immaculate after all. 2. The Milky Way is not just a hazy band of light. Galileo found that each tiny speck in the Milky Way was actually a star. This meant the universe was far vaster than anyone had imagined, and the number of stars far beyond human comprehension. 3. Jupiter has 4 small moons orbiting it. This directly undermined the geocentric model. It turned out not all celestial bodies revolved around the Earth. 4. Venus's brightness changes periodically, like the moon's phases. This indicated that Venus likely orbited the Sun, not the Earth. Copernicus's heliocentric theory had existed before, but it was a niche idea. Galileo's findings strongly supported heliocentrism with direct evidence. Once you put all these discoveries together, you're forced to accept that Earth is not the center of the universe. Going further, you might guess that the Sun is nothing special either, that perhaps every star is a sun with its own planets, and that there may be countless worlds like Earth. I often think of the Starry Messenger. I envy Galileo, but I envy even more the literate people of his time. Those who, having firmly believed Earth to be the center of the cosmos, suddenly realized there might be other Earths. What a shock that must have been. The book caused heated debate among scholars, made the church extremely nervous, and created a sensation in society. European nobles and merchants rushed to buy telescopes. Astronomical observation became a refined, fashionable activity among the upper class. Today, scientific progress is cumulative, incremental, and slowing. Our worldview is stabilizing. We may never again see a book so shattering to our perception. Galileo's discoveries were only the prelude. Other astronomers quickly adopted the telescope, and heliocentrism soon took root. Kepler, within a few years, discovered that planets travel around the Sun in ellipses rather than perfect circles. Galileo also derived the law of free fall from experiments. Yet neither he nor Kepler knew what it all meant. The true revolution had to wait for Newton. In 1687, Newton published Philosophiae Naturalis Principia Mathematica. Every physics teacher will tell you it laid out the framework of classical mechanics, introduced the law of universal gravitation and the 3 laws of motion, and explained planetary orbits. But they may not tell you its greatest significance. Newton's Principia told us that the world is lawful. Apples fall not because they want to, or because some deity commands it. Planets orbit the sun not because angels push them. They do so because physical laws require it. From apples to Jupiter to humans to the entire cosmos, everything must strictly obey the same physical laws, without exception. And those laws can be written in simple mathematical formulas. 3 basic principles, 1 formula for acceleration, 1 for gravity. Done. From these 2 equations, you solve the differential equations, and you get the planetary orbits exactly right. Has there ever been a greater discovery? Everything exists and behaves not because it happens to, and not because God individually arranged it, but because there is an underlying set of physical laws expressible in mathematics that determines it must be so. The workings of the world follow patterns, with clear cause and effect. Newton embodied the ancient ideal of establishing the mind for heaven and earth, comprehending the transformations of past and present. Newton's theory utterly transformed humanity's worldview. He didn't just launch modern science. He launched the age of reason. Because of Newton, mathematics became truly exciting, enabling Euler, Laplace, Lagrange, Fourier, inspiring Kant and other serious philosophers, fueling the Enlightenment, paving the way for the modern world. Newton's spirit was that humans can understand the world, and to some extent predict and control it. This liberated humanity from the fog of not knowing which God to trust, and gave us a sense of ownership over our fate. For a time, Newton made us think the world ran like clockwork, purely mechanical, with no room for chance. Which may not be right, but that's another story. If heaven had not produced Newton, the world would have remained in darkness forever. For nearly 2 centuries after Newton, physics advanced slowly. The laws of mechanics had theoretical value, but people didn't solve differential equations to build bridges or houses. Mathematicians played endlessly with Newton's theory, but experimental tools were limited. Observations were still mostly of the heavens. The Industrial Revolution, with its steam engines, inspired physicists to develop thermodynamics, but that was practice feeding science, not science guiding practice. It was electromagnetism that truly gave science economic value. Coulomb, Ampere, and Faraday investigated electric and magnetic phenomena, but the true master was Maxwell. In 1865, Maxwell unified electricity and magnetism into 4 elegant equations. 1. Electric charges produce electric fields. 2. There are no magnetic charges. 3. A changing magnetic field produces an electric field. 4. An electric current or changing electric field produces a magnetic field. The magical part was the last item, that a changing electric field produces a magnetic field. Maxwell added it purely for mathematical completeness. No one had experimentally observed it before. Later, experiments confirmed it. This was the first time in history a physicist deduced a law of nature purely from theory. Theory said it should exist, and experiments found it did. This is the highest achievement a physicist can have besides Newton's own feats, a privilege later shared by only a few, including Einstein, Dirac, Gell-Mann, and Higgs. Even more remarkable, Maxwell's equations predicted electromagnetic waves, and revealed that visible light itself is an electromagnetic wave. Afterward, Edison and Tesla ushered in the electrical age. Hertz confirmed electromagnetic waves in 1887, and by 1895 humans were using wireless communication. Physics' worldly triumph. But Maxwell's deepest contribution to our worldview was the concept of the field. Space, it turned out, is filled with unseen electromagnetic fields. Objects interact not directly with each other, but through these fields. I dare say that later Qigong masters, talking about energy fields, were inspired by this. The key point: space is suffused with a structured, measurable form of energy and information. The world had another hidden side. Once physicists had electricity to play with, they could perform more intricate experiments. By the early 20th century, physics surged forward. 100 years ago, physics was like AI today. New discoveries almost daily, brilliant figures emerging constantly. But even more dramatic, physics repeatedly shattered our worldview. We've already discussed relativity and quantum mechanics elsewhere. Here, let's focus on their impact on ordinary people's perception. Einstein's relativity, starting from the counterintuitive but unavoidable assumptions of the constancy of the speed of light and gravity is equivalent to acceleration, told us that spacetime is not just a concept but something real. Spacetime has shape. Time can speed up or slow down, space can curve. Quantum mechanics, created by Bohr, Schrödinger, Heisenberg, Dirac, and others, told us the microscopic world is utterly unlike our everyday experience. Electrons can be here and there at once, passing through two slits simultaneously. The world is fundamentally random. Things can happen for no reason. Particles can temporarily violate energy conservation, and tunnel through barriers. They can even appear from nothing in a vacuum. Two particles, no matter how far apart, can be mysteriously entangled. Each of these ideas is worth retelling to every generation, because we still don't know why the world is like this. And all of these mind-bending ideas were known to physicists before World War II. Physics has progressed since then, but the shocks to our worldview have been smaller. In the 1940s, Feynman and others perfected quantum electrodynamics, QED, which can explain all phenomena except gravity and nuclear forces. In the 1950s, Young and Mills developed gauge field theory, providing the mathematical foundation for studying interactions inside the atomic nucleus. To make a long story short, by the 1970s physics had a unified theory explaining everything except gravity, the Standard Model. Its worldview. 1. Everything is particles. Or equivalently, everything is fields. Particles are excitations of fields. Think of photons. Light is an electromagnetic wave, i.e. the electromagnetic field. Quantum mechanics says light comes in quanta, photons. QED merges these. Photons are quantized excitations of the electromagnetic field. Similarly, electrons are excitations of the electron field. 2. All particles fall into three categories. Matter particles. Quarks and leptons. Quarks form protons and neutrons. Leptons include electrons and neutrinos. Force carriers. Photons for electromagnetism, W and Z bosons, for the weak force, gluons for the strong force. A single special particle. The Higgs boson, the quantized excitation of the Higgs field, which gives other particles mass. 3. There are four fundamental forces, interactions. Electromagnetism, the weak interaction, responsible for beta decay, the strong interaction, binding quarks into protons, neutrons, and nuclei, and gravity. Gravity lies outside the Standard Model, handled by general relativity. The Standard Model plus general relativity can explain almost everything. That's the worldview physics reached by the 1970s. In the 40 to 50 years since, general relativity has given us gravitational waves, and quantum mechanics has spawned semiconductors, lasers, quantum computing. But our worldview remains the same. Many physicists, unwilling to accept this, have proposed all sorts of exotic theories, but none have held up. I think this is the wall. It's a wall, not an absolute end, because we know there must be something beyond it. We'll talk about that next time. That's it for today's content. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.